In this video, we'll use perturbation theory to compute the relativistic correction for the hydrogen atom. We'll start with talking in general about corrections for the hydrogen atom. And then we'll talk about the first order relativistic correction, then the relativistic energy correction, and finally we'll talk about why we don't use degenerate perturbation theory for this particular case. So, the fine structure of hydrogen is a correction to the exact solution that we gave before. The Hamiltonian that we solved exactly for the hydrogen atom was just an approximation. The first order correction is that you have to have motion for the proton added in, because we assumed that the proton was fixed in space, and in fact that's not a correct assumption, because the proton is not infinitely more massive than the electron. So we do that by, instead of using the electron mass, we use a reduced mass mu. So we can replace the electron mass with mu, which is the mass of the electron times the mass of the proton divided by the sum of those masses. And of course, because the electron is about 2,000 times less massive than the proton, this is going to be heavily weighted towards the mass of the electron. And in fact, this becomes 1836 divided by 1837 times me. So really, it's a correction of about 1,000th, or 1/2000th. Another important correction, the other important corrections can be scaled according to a constant called the fine structure constant, alpha. Alpha is equal to the electron charge squared divided by 4 pi epsilon naught h bar c, and it's approximately 1/137. So, some of the relevant corrections that we know about are the Bohr energy, which is the sort of the energy of the hydrogen atom ground state, goes like alpha squared mc squared. The fine structure constant, which is what we're going to be developing starting today with this video, goes like alpha to the 4th mc squared. So since this is about 10 to the minus 2, this is about 10 to the minus 4 compared to the energy. It's a correction on the order of 1/10,000th, or less than 1/10,000th. We then have the Lamb shift, which goes like alpha to the 5th times mc squared. And then the hyperfine correction, which goes like alpha to the 4th times mc squared, but there's an additional term that's approximately the mass of the electron divided by the mass of the proton, which is about another factor of 2,000. So it's another 1,000 down from the fine structure. So typically, we're going to start calculating the fine structure, and then we'll add in the hyperfine structure. So the largest correction to the hydrogen atom is in fact the fine structure. And the fine structure consists of 2 terms. Today we'll talk about the relativistic correction. In the next video, we'll talk about the spin orbit correction. So the first term in the Hamiltonian, our regular Hamiltonian, that is p squared over 2m, is usually taken to be the kinetic energy. And this is fine for classical particles, but for relativistic particles, this isn't correct. Instead, in order to get the kinetic energy, you have to subtract the rest energy from the total energy of the system. The total energy is given by gamma mc squared, where gamma is a relativistic gamma, which is equal to 1 over the square root of 1 minus v squared over c squared. And so this depends on the velocity, right? On the velocity of the particle. And the rest energy is just mc squared. So gamma goes towards 1, and it becomes 1 when you're non-relativistic, and it becomes bigger than 1 when you're relativistic. So we can generate a better correction, or an expression for the kinetic energy that is now not p squared over 2m, but it's more complicated than that. And it's not as convenient as writing it like this. We have to transform this into something that's more useful. We can obtain this by starting with the energy-momentum relation from special relativity. The energy-momentum relation says that E squared, the total energy squared, is equal to the momentum times c quantity squared plus the rest mass squared. Well, if we just multiply that out, it's p squared c squared plus m squared c to the fourth. So, if we now take the total energy, which is E, and subtract the rest mass, we have to take this quantity square root minus mc squared. And so that's what I've written up here. I have square root of p squared c squared plus m squared c to the fourth minus mc squared. And that's now the kinetic energy. We can now expand this expression in powers of p over mc. So if I divide this by mc, I'm going to get that the kinetic energy is equal to mc squared. Right? I can pull the mc squared out of this because that's this squared. So I pull that out. I have an mc squared here. That gives me the 1. And the square root then becomes 1 plus p over mc quantity squared. And this is p over mc because one of the c's is canceled out by the c that goes along with p. Well, if we assume that this is small quantity compared to 1, then we can expand this. And we'll expand this using the binomial expansion for the square root. So that gives us 1 plus 1/2 p over mc quantity squared minus 1/8 times p over mc to the fourth. And then you have additional terms and then a minus 1 at the end. Well, clearly this one cancels this one, and we're left with just the terms in here, which gives us, when we multiply this out, you have mc squared times this quantity here. So unfortunately, I've dropped the mc squared. You have mc squared times p squared over 2m minus p to the fourth over 8 m to the third c squared. And then additional terms that are higher order. Now, clearly, this reduces the classical expression. I'm sorry, no, this is, the mc squared is brought in here and it cancels out. So when it cancels out, it gives you p squared over 2m, p to the fourth over 8m cubed c to the c squared. That's canceled out one of the m's and 2 c's. And so when you look at these terms, the first term is simply the classical Hamiltonian for kinetic energy, p squared over 2m. The second term must be the relativistic correction to first order for the momentum and to the kinetic energy. So this is the first order relativistic correction. We now call that our perturbing Hamiltonian, right? So this is the relativistic H prime, which is the perturbing Hamiltonian, which will give us the expectation value of which will give us the first order energy correction to the relativistic correction. Well, that's simply, you have a bunch of constants, so it's minus 1 over 8m cubed c squared. And then you have the expectation value of p to the fourth, which is what's on top. And of course, this is an operator, but since p squared is a Hermitian operator, we can move it over to this side and we can remake this as the expectation value of p squared psi, which are two identical functions. So as we start with this is the energy, the first order energy correction, which is the expectation value of this p squared psi, and then some constants in the front. We can evaluate this by rewriting the unperturbed Schrödinger equation to extract what p squared psi is. Well, we start by writing down the Hamiltonian. H psi is equal to p squared over 2m psi plus v psi equals e psi. we can rewrite that as p squared psi. So the operator p squared applied to psi is equal to 2m e minus v all times psi. And so that says that the first order relativistic energy correction is minus 1 over 2 mc squared. Take this out, right? Then we have the expectation value of E minus V quantity squared. And so that becomes 4m squared, which cancels a bit of this 8m cubed to leave us 2mc squared in the bottom. So this expectation value, E minus V, well, E is just a constant, but V is the potential for the hydrogen atom, which we know is the Coulomb potential. So we now can expand this, and we get minus 1 over 2 mc squared times the quantity E squared, which is just the energy of the Bohr atom, unperturbed Bohr atom, minus 2E times the expectation value of V, plus the expectation value of V squared. If we now substitute our expression for the Coulomb interaction in for V, remember that's minus 1 over 4 pi epsilon naught r times E squared. Then we have that the energy correction is minus 1 over 2 mc squared E sub n squared plus 2E sub n times the quantity E squared over 4 pi epsilon naught times the expectation value of 1 over r. And then you have a third term, which is E squared over 4 pi epsilon naught quantity squared times the expectation value of 1 over r squared. So what it boils down to is that we replace now the energy with E sub n, so that's the energy of the specific state that you want to calculate the correction for. So this is E squared sub n, and then E sub n here. And we substitute the potential for the hydrogen atom. So E sub r, first order correction, relativistic correction to the energy, depends on two expectation values. The expectation value of 1 over r and the expectation value of 1 over r squared. So this is our expression for the relativistic correction. I'm not going to do the calculations for these two expectation values. These are done in problem 742. And when you work that out, you get the following expressions. The expectation value of 1 over r is just E squared m over 4 pi epsilon naught h bar squared. And the expectation value for 1 over r squared is E squared m over 4 pi epsilon naught h bar squared, quantity squared, times 1 over L plus a half times n cubed. If I now put those two values in to my expression for the relativistic energy correction, I get E sub r, first order correction, is equal to minus 1 over 2 mc squared times the quantity E sub n squared plus E sub n times E squared over 4 pi epsilon naught quantity squared times 2m over n squared h bar squared. So you can see what how this came out here. And then the second term, or the third term, is E squared over 4 pi epsilon naught to the fourth power. And then we have m squared over L plus a half n cubed h bar to the fourth. And this now allows us to write down the final relativistic energy correction. If you recall, E sub n is equal to minus m over h bar 2h bar squared, E squared over 4 pi epsilon naught squared times 1 over n squared. So this term here is directly related to E sub n. And this term here goes like E sub n squared with an n on the top. And we can put that all together. We get that the relativistic energy correction first order relativistic energy correction gives you minus 1 over 2 mc squared times E sub n squared minus 4 E sub n squared plus E sub n squared times 4n over L plus a half, where L is the orbital quantum number. This all collapses into a very simple expression, which gives us minus E sub n squared over 2mc squared times the quantity 4n over L plus a half minus 3. And so the relativistic energy correction goes like the energy squared divided by 2mc squared, and then a bunch of integers. So this correction is about 2 times 10 to the minus 5 smaller than the characteristic energy of the state. Right? So this correction ends up being 2 times, almost 10,000 or 200,000 times smaller. So we did this using non-degenerate perturbation theory, right? We just calculated the expectation value of the operators and assumed that would be the energy correction. But we know that the hydrogen atom states are highly degenerate because with L not equal to 0, if L is equal to 1 or 2 or 3, then you have high degeneracies. And those degeneracies would give you a problem if you were doing first order perturbation theory. So why did we use first order perturbation theory? Well, the reason is that you can find good states for your perturbation theory, for degenerate perturbation theory. If you have the good basis set, then your degenerate perturbation theory problem just reduces to a non-degenerate first order perturbation because you already have diagonalized the perturbing matrix, right? So by finding the right basis set, you diagonalize H prime, and diagonalizing H prime means that the correction, it just is what's on the diagonal of the H prime matrix. Well, in this case, H prime, H sub r prime, is equal to minus p to the 4th over 8m cubed c squared. And the operators that we want to diagonalize are the L squared and L sub z because the result depends on the orbital angular momentum, as you saw in the previous slide. So if we look at the commutators of all the relevant operators, the question we want to ask ourselves is, does L squared commute with H prime r? Does L sub z commute with H prime r? But this is basically the kinetic energy operator squared with some constants involved. And so, in fact, it does commute. So the H prime r commutated with L squared is equal to 0. And similarly, the commutator of H prime r, H sub r prime, is with L sub z is also equal to 0. And because of that, we already are in a good basis set. The basis set where we have quantum numbers for the principal quantum number n, L for the orbital angular orbital quantum number, and m for the magnetic quantum number are already good states. The spherical harmonics are already good states for this p to the 4th power Hamiltonian. So the eigenfunctions, therefore, the psi NLM are already good basis set for this perturbation, and because they're a good basis set for the perturbation, it's already diagonalized, and we can use first order perturbation theory. That's not going to be necessarily the case for all perturbations in the hydrogen atom.